to my home in Selsey. Tonight's programme is about my own special subject, the moon, a wonderful world of mountains, valleys, craters and waterless seas. You know, when I was young, it seemed so inaccessible. Now, men have been there, new missions are being planned, and a lunar base is a real possibility. Well, tonight, a very special night. A total eclipse of the moon, the last world seen until the year 2015. Outside, near my observatory, all kinds of people are gathering. Amateur astronomers, professionals from all over the world, with their various bits and pieces of equipment. I'll join them shortly. Meanwhile, Chris Lintott is with them.
Patrick spent literally thousands of nights observing the moon with this telescope, but tonight we hope to use it to view a lunar eclipse. At 12:36, the moon will start its passage through the Earth's shadow, and we reach totality a couple of hours later at 3 o'clock. During the last total lunar eclipse, back in March 2007, we saw the moon go a deep red colour, and we're hoping for more of the same tonight. So Pete, what is a lunar eclipse?
Okay, well, a lunar eclipse occurs when the moon moves into the shadow cast by the Earth from the sun.
Okay, so we've got Sun, Earth,
and the moon.
We're down here in Selsey, so tonight, what are we going to see? Right,
well, the first thing that happens is where the edge of the Earth starts to clip into the sun's disk, the lunar surface starts to dim slightly.
And that's the penumbral phase,
that's
a very
right.
faint dimming of the lunar surface.
It is a faint dimming and it's very difficult to see. Visually it's almost impossible to see. If you've got specialist equipment you can start to detect it. And then as we move into about 1:43 our time, we start to see this main part of the shadow creep across the moon's surface until the moon eventually ends up completely in darkness.
Totality.
Totality, and that's about 3:01. The reason why it's reddish, by the way, is because red light goes straight through, the blue light is scattered out of the way.
So the moon goes around the Earth once every 28 days. Why don't we get an eclipse every month?
That's a very good question. The reason is because the moon's orbit is inclined to the orbit of the Earth around the sun by about 5 degrees. And that means that the moon comes round and it will either go below or above where the Earth's shadow is. But when you get this rare line up, you actually get the moon going into the shadow and then we get a total eclipse of the moon.
These are some of my old moon globes, going back to 1958-59. They're Russian ones, actually. And as you can see, part of the surface is not shown. We can't see it from here. It's always turned away from us. And not until the rockets went round the moon did we get good views of it. Even now, you know, we've now had good views of the moon's poles. And the Americans are now planning to have a long, hard look at the moon's south pole in their project L-Cross. Chris went to California to get the latest news.
This is NASA's Ames Research Center. It was here that the samples from the Apollo missions were first analysed, and today they're involved in the next steps of our exploration of the moon. L-Cross, the Lunar Crater Observation and Sensing Satellite, is a cheap, quick mission for NASA with maximum impact. Its target is the moon's south pole. Crashing into the moon is something of a space tradition. The Ranger spacecraft collided with the lunar surface in the 1960s, and the Russians had their fair share of collisions with the Lunik missions. Even the Apollo missions sent their rocket stages into the moon to set off moonquakes that were detected by instruments the astronauts left on the surface. The last stage of this mission's rocket will crash into the moon, creating quite a bang. L-Cross, a small observation satellite, will follow a few minutes behind, watching and then flying through the debris cloud before it too hits the moon.
I like to compare it to a prospector. We're near San Francisco, which is famous for its gold prospecting in the late 18th century. They were cheap, they were poor, they had to find inexpensive ways to prospecting for gold, so they take dynamite, put it in a crack in a gully, blow out a hole, slew the dirt and pan for gold to find a vein. We're doing something pretty similar.
But it's not gold L-Cross is hunting, it's water. In 1994, the Clementine mission discovered concentrations of hydrogen at the lunar poles. Some believe that this tantalizing discovery could be the signature of water ice, lurking within cold, dark craters that never see the sun. Alcross should settle that argument once and for all.
The North Pole has smaller craters than the South. The South has some very old, ancient, large craters. Shoemaker, for example, is about 35 kilometers across. Faustini is 30 kilometers across. These are old, 3 billion year old craters, easily targeted. So that's primarily why we went to the South Pole. We know there is hydrogen there. There's every reason to believe that temperatures are very cold. So these cold polar traps should be fantastic places for the deposition of volatiles of all sorts, not just water, but carbon dioxide, sulfur dioxide, methane even. And if we can actually establish that these volatiles are indeed being trapped in these cold craters, they're acting as time capsules for the formation and the evolution of the inner solar system.
If there is water on the moon, it could have come from comets or be left over from the time of the moon's formation. More than 4 billion years ago, a planetoid the size of Mars collided with the young Earth. Over millions of years, it's thought that debris from Earth and from the original impactor coalesced to form the moon. The early solar system was a violent place, and soon after the moon's formation, its surface was bombarded with asteroids and comets, creating the craters that we see today. Things have quietened down since then, so scientists working on Alcross are forced to create their own impacts. Alcross is going to need a lot of mass if it's going to make an impression on the lunar surface. Luckily, the Centaur rocket stage is the size of this bus behind me. It'll be travelling at more than 5,000 miles per hour, so it should make quite a bang. Ames still shares its site with a large Navy base, so target practice is nothing new. The Alcross team can't practice crashing into the lunar surface, but they can do the next best thing. Since the time of Apollo, engineers have been using this equipment to make their very own craters.
So Chris, this is the big gun. This is what we're going to use to simulate what's going to happen for Alcross. This is the gun that allows us to fire a bullet into something that would simulate the moon, and then we watch the ejecta come out of the surface, and it gives us a much better idea on how much material will come off, and perhaps if we'll have any volatiles released from the polar regions.
And it's an impressive piece of kit. Take us through it.
Sure. Let's start over here. This actually uses about a lot of gunpowder that explodes, and then we'll take a tube, a cylinder, and compresses hydrogen gas up to about 1 million times typical atmospheric pressure. It will then take a projectile that's embedded within a sabot, a small carrier, and it comes flying down this launch tube and then eventually into this chamber, keeps on going down this range where it is recorded by a series of lasers and cameras, and then enters into the large chamber. And that large chamber is where the business happens.
These crater floors, Alcross's targets near the South Pole, are permanently shrouded in darkness, potentially allowing ice to survive. If there is water on the moon, it will be here.
Now we're looking from above as if we're following the projectile as it was heading into the moon.
And the first thing you see is nothing.
Right, it's just dead black. But then we had the flash. That's the moment of impact. And now we see that heated material, then suddenly we begin to see material coming into the sunlight.
So this has been thrown up enough that it's into daylight and we see the scatter.
Now the ejecta is rising above that rim of the crater. And you notice that we still see some hot stuff on the floor.
How long is it between the flash and the end of the material being thrown up?
It could be as long as 10 seconds. It could be less. Really, it depends on how deep in the shadows.
As much fun as blasting a new crater on the moon is, it's the science afterwards that's really exciting. The shepherding satellite, which separated from the rocket prior to impact, will have just a few minutes to analyse the dust cloud from the explosion. Tony took me into the clean room, where the cameras for the satellite are being tested, getting ready to study the impact in different wavelengths.
We've got a suite of cameras, 5 of them, and you can see them here in the payload observation deck. The first camera, the one running along the diagonal there,
just over to the left.
To the left is the visible camera. It tells us where we impacted, gives us the visible imaging of the ejecta cloud. Below that you see 2 cameras. The larger of the 2 apertures is a filtered near-infrared camera, and the one to the right of it is another near-infrared camera. The 2 cameras are different only in that the one is filtered so that water ice or liquid water is accentuated in the image. So for example, using a bottle of water like this, one camera will see the water more distinctly than the other camera because of that filter. And then when we difference those 2, you should clearly see where the water is actually in this camera shot in the bottle.
So far we've detected water on the Earth. That's a good start. Let's go and see if it works on the Moon.
Exactly, and we'll be thrilled if there's actually this much water.
Once the rocket hits the Moon, as in any explosion, things will happen very quickly. The shepherding satellite won't have long to gather its vital information.
Really, the scientific meat in the mission is about 30 seconds long. The entire lifetime for this payload during the impact period is 4 minutes before it itself impacts the Moon. But following impact, the next 30 seconds following the impact, that's the most important time. That's where we're going to answer all of our most important fundamental questions. So yeah, it's a lot of work for a short amount of time.
The Alcross mission launches in October alongside its bigger sister mission, Lunar Reconnaissance Orbiter. Alcross won't hit the Moon straight away, as it needs to increase its speed to achieve maximum impact. So after various slingshots around the Earth and the Moon, it will hit the Moon early in 2009, when the world will be watching.
We believe it's going to be about a magnitude 6.
So certainly binoculars then will see this flash.
Yeah, and the flash may not be visible because it may be hidden below the rim of this shadowed crater. However, this cloud is what we expect most people to see. So you'll see this twinkling rise above the lunar limb of the South Pole and extend down several arc seconds at least, so it should be quite visible.
Since we filmed, the payload has been tested and shipped out to fit onto the spacecraft. If Alcross's prospecting is successful, and it does discover substantial deposits of ice, then future astronauts will find many of the supplies they need already in place. Planning for man's return to the Moon will have made another giant leap forward.
Well, the search for water ice is on. Do you remember Beagle 2? Well, recently, NASA scientists went to Milton Keyes Open University to talk to the scientists there to see whether instruments based on those of Beagle 2 can be used to look for water ice on the Moon. And I went there to meet them.
Okay, well this is the model of the Beagle which was sent to Mars in 2003. If you start lifting the lid, you'll see it folds over. And there's a...
Beagle 2 was meant to be working on Mars, sending him information about the Martian rocks and soil, and even looking for life. But when it landed in Christmas 2003, something went badly wrong, and it never sent back any information. The instruments on board were the very latest complicated laboratory analysis equipment, miniaturized and licensed for space.
Then if you want to analyze samples, you can put it down on the surface.
So 4 years on, Colin is delighted to be showing his instrument to 2 NASA scientists who are interested in using it for future of robotic and manned missions on the Moon.
It vindicates our investment, if you like, that NASA has recognized that the technology that we included could be used to prospect for water. And it would be very nice for me personally, since you and I have been talking about the Moon for 35 years at least, it'd be nice to go back to the Moon at the end of my career.
How much of the original Beagle are you using?
Nearly all of it. Nearly all the scientific parts of it are appropriate. The whole kit is absolutely perfect for doing chemistry, mineralogy, taking photographs of the rocks. The mole is able to burrow underneath the surface, which would be a cold spot. It would trap down volatiles. The organic analysis part of Beagle would be usable to see if there's any cometary volatiles trapped out. And I worked on the Moon and Apollo, so I know that the solar wind produces volatile species such as water and methane in small amounts, but remember we're integrating over 4.5 billion years on the Moon. The gas that comes out of the samples is processed by this unit here that looks a little bit like a Ferrari V10 engine.
The instruments on Beagle 2 were unique. Engineers and scientists at the Open University designed and built this mass spectrometer to measure isotopic compositions on Martian soil. Scientists Dr. David Mackay and Everett Gibson are working out technology NASA doesn't have. On the Moon, this will analyse lunar samples looking for water ice and other volatiles.
What we would like to do is use some of the technology that Colin and his team put together and use it to take it to the Moon. We understand what the Beagle can do, that we need to, of course, modify it because we don't need the aeroshell because we'll be deployed by an astronaut. But what we're really interested in is to have the tools of the gas analysis package, which is inside the Beagle 2, to seek the signatures of water.
We talk about water on the Moon. So people like me are highly sceptical, but what do you think? Is there water there? If so, can we extract it?
Well, I'm skeptical also about finding liquid water on the Moon, but we have the ingredients for water on the Moon.
What about ice?
Well, there could be ice in the permanently shattered areas of the pole, but the surface of the Moon is constantly bathed and irradiated from hydrogen atoms that come from the sun and the solar wind. And these implant the outer micron into the outer microns of every grain, soil, rock. And we know that we can get this hydrogen out. If we take 1 square meter of lunar soil, there's enough hydrogen that can be extracted to give you 8 ounces of water. Here we have orange juice, but yet water is the ingredient. So we can recover water from the lunar regolith, but it's from a form of hydrogen from the sun.
Well, if any water is found there, or ice, I for one would be very surprised.
Well, I tend to agree with you, Sir Patrick. I think that it's more likely solar wind, but I'm very open to it. That's why we have to go there and find out.
It could be a key driver in the long-term stay of humanity on the Moon. That would assist us living off the land, in this case the land, the Moon, and the volatiles and water that have come from meteoroids and comets over millenniums.
The Beagle instrument is currently under study by NASA. If it is selected for further developments, then it could be used on future robotic missions and even carried around by astronauts. If that happens, Colin and his team really will be over the Moon. Let me turn now to a very exciting project, Moonlight, in which we are involved. And welcome now to Sir Martin Sweeting from Surrey and Dr. Ian Crawford from Birkbeck College. Welcome to the Sky at Night. Martin, some people won't have heard about Moonlight, so could you give us a general rundown, what it is, what's it going to do, and when will it start?
Well, Patrick, it's a very exciting project because it's going to be a UK mission to the Moon. It's going to be a satellite which is launched into polar orbit around the Moon. It is going to carry some onboard communications and navigation experiments to provide a sort of, if you like, an internet around the Moon, and to provide sort of GPS signals around the Moon to help future missions that are going to land on the surface.
Part of a purely international project.
Absolutely. So it's going to be UK-led, but there are going to be international partners. Possibly NASA might participate. And then alongside the communications systems and navigation systems, we're going to carry some science payloads. And hopefully all of this will be launched in about 2013.
Ian, what about the immediate science?
Well, the Moonlight spacecraft is to carry 4 penetrators, as we call them, which are basically 4 darts, meter-long darts, which will be dropped from lunar orbit and bury themselves into the lunar surface. And this is a very efficient way of emplacing certain scientific instruments, especially geophysics packages. I can demonstrate on this Moon, actually. The plan would be, on this lunar globe, the plan would be the Moonlight orbiter will be in a polar orbit, and the Moon will turn underneath the orbit. And then the spacecraft will drop in these 4 darts, And currently we envisage dropping one in at North Pole, one at the South Pole, where no data has ever been returned from the polar regions of the Moon to date, one into the centre of the far side, from which also there's no in situ scientific data ever been returned, and one into the centre of the near side, somewhere within the region of the Apollo landing site.
How deep will these darts go?
Well, they should bury themselves approximately 3 metres into the lunar soil, and then they will operate for about a year. And in particular, they will carry seismometers, which are devices to measure moonquakes, which will help us determine the interior structure of the Moon, whether it's got a core or not, whether that core is liquid or molten or not, and help make a number of other geophysical measurements that the Apollo missions 40 years ago were unable to do.
Well, when we say strong moonquakes, well, in Japan you wouldn't notice them.
No. The Apollo seismometers were fantastically sensitive instruments, and the vast majority of them you would not notice. On the other hand, these relatively rare, unexplained so-called shallow moonquakes are the strongest. I believe, if memory serves, the strongest detected during the 8 years the Apollo seismometers remained active was a magnitude 5 quake.
That was near Aristarchus.
Well, from an engineering point of view, building a moon base, you would want to know whether your moon base is likely to have to experience that kind of seismic event, so you can engineer your outpost to withstand it.
And above all, I think moonlight keeps us right in the space programme. Otherwise, we might be outside it.
Oh, I think there are multiple roles that the UK can contribute. I mean, there is currently a renaissance in lunar exploration. Yes. There are half a dozen spacecraft either in lunar orbit or will be within a couple of years. But all of these are orbital instruments. They're sensing the Moon from orbit. There hasn't been in situ surface science done on the lunar surface since 1976. So what the UK has an opportunity here is to participate in the first in situ direct science on the lunar surface for a generation. And I think in terms of developing the UK planetary science community, such that in the fullness of time we can play a larger role, this is absolutely a fantastic opportunity.
Can we please now look a bit further ahead? We talked about lunar bases and men on the Moon. If so, where's the promising site? Shackleton Crater?
The current planning, the US planning for return to the Moon, does envisage setting up a base on the rim of Shackleton Crater. Shackleton Crater is a 19-kilometre diameter crater almost exactly at the south pole of the Moon. And for the initial setting up of a lunar base, which would presumably require solar power, certainly initially anyway, this means you've got the longest possible duration of daylight to power your base and scientific instruments occurs at the poles of the Moon. Now that's an operational reason, almost permanent sunlight, but of course the south pole of the Moon is scientifically very important as well, because no missions have gone to the South Pole yet. It's within or on the edge of a huge impact basin called the South Pole Aitken Basin, which is very important to explore scientifically. So these are the reasons that are driving people to plan for an initial outpost close to the South Pole of the Moon, and the rim of Shackleton in particular, because it's got very good solar illumination.
Well, we've been talking about the Moon, and this is going to be a long and exciting night. We have a total lunar eclipse. So now, out to my observatory where things are getting ready.
Well, the sun has set, it's dark, the moon's there, and although there's some cloud around, we're hoping conditions will be good for the eclipse, which starts in a couple of hours' time. It's not quite as clear as it was for last year's eclipse, which was really spectacular.
What we hope to do is capture the progression of the eclipse and the colour as it changes from its normal bright whitish grey colour to this beautiful coppery red, which is kind of
or whatever colour it's going to go.
Whatever colour it's going to go. We don't know yet, but we hope we'll get to see it anyway.
I think it's our common duty to come out and watch things like this. It's a very gentle celestial show. And doesn't that look beautiful right now?
It's nice. It's nicely framed with the cloud, isn't it?
Yes, it's just a moment of sheer joy to look at it.
And you never quite know what colour it's going to be until you reach that totality, do you?
No, that's right. I mean, it really does change when it gets total. And the one last year, the stars came out beautifully. I seem to remember it got quite dark.
This is Patrick's boyhood telescope, and even a small telescope like this one will tell you a lot about the moon. You can see the seas, the craters, and from these clues piece together the history of our nearest neighbour. As the moon orbits the Earth, going round once every 28 days, it appears to keep the same face turned towards us. This alignment is the result of friction caused by the Earth's gravitational pull on the moon, but it isn't perfect. The moon does wobble slightly, allowing us over time to see slightly more than half the surface. As the month wears on from new moon towards full moon, we see the dividing line between night and day, the terminator, creep across the surface. Features such as craters are best seen when they're near the terminator, when light from the rising sun casts long shadows. Others, like the rays that stretch out from the largest craters, need the sun to be overhead to be really well seen. Well, you can tell a lot about the moon even with a small telescope like this. The first thing you notice is it's got two colours on it.
Absolutely. So the white areas of the moon are the highlands. So these are originally what was called the terre regions of the moon. And these are actually the remnants of the really primary early products of when the moon formed. So they're really, really ancient. The darker areas are called mare regions. These were originally thought to be seas by early astronomers. And these are actually much younger lavas that have flooded into the highland areas. And what else we can see on the moon, which is really interesting, is craters. The whole of the surface of the moon is covered with craters from all different scales and size, from hundreds of meters up to thousands of kilometers across. Now, there's been a big debate all through kind of lunar observations about whether these craters were formed through volcanism, so whether they were formed in eruptive events, or indeed whether they were formed from impacts.
From meteorites?
Yeah, absolutely. So from meteors hitting into the surface of the moon. And we now know definitively that the vast majority of them are formed from these impact cratering style events and not from volcanoes at all.
And in fact, this is the best record we have of the number of impacts that the Earth would have suffered over the last few billion years.
Absolutely. So the impact record on the moon is preserved from 4.5 billion years ago. So in fact, not only does it track, as you say, a history of what's been going on the moon, it tracks a history of the entire inner solar system, so of the terrestrial planets as well.
I've been observing the moon now for over 70 years. And now, welcome back to one of our most regular visitors, Dr. Alan Chapman. Welcome
Always
back.
a pleasure, Patrick.
You know, lunar observation goes back a long way.
It does indeed. In fact, it was Thomas Harriot, an Englishman, who first made the observations of the moon in the summer of 1609, slightly ahead of Galileo.
Yes, indeed.
But right from the word go, people were fascinated by the moon because it looked rather like the Earth.
Yes,
and
indeed.
in fact, several people commented that it looked rather like a book of Dutch sea charts with islands and bays and all sorts of things. And people even speculated whether people were living on it in the 17th century.
Right. And of course, maps came later, and names came with them. Riccioli in 1651.
They came absolutely that way. And they came particularly, of course, with people like Johannes Hevelius, the great Polish lunar cartographer. And of course, he started to map the moon to a remarkably high standard.
Then we have the names by Riccioli.
And the names, of course, were usually those of great Greek philosophers. So very early ones would include people like Ptolemy. But of course, too, they recognised the great moderns, as they called them.
Well, Newton came off very badly.
Newton came off very badly because he was a little bit too late on in the game. He'd mapped most of the moon by his time, you see. But of course, look what a whopper Copernicus gets, and what a whopper Tycho Brahe gets. And of course, the people of the 17th century saw Copernicus and Tycho as creating the new modern astronomy.
But Riccioli didn't like Copernicus. He didn't believe Copernicus, so he flung Copernicus into the ocean of storms.
Absolutely.
Where he is now.
But it was nonetheless a pretty spectacular crater
lovely,
in the ocean of storms, and it must have made quite a splash when it landed
It
there.
must have done. Enough. And we have these various types of features. We have the rills or clefts, the long crack-like things. Have the mountains, which are mainly the borders of the circular maria, and the seas, but never were seas.
And then in the 19th century, you have people like James Naismith, the Scottish Manchester engineer, an experimentalist, and he's suggesting that the moon might have been volcanic.
Well, there was that great debate, were the craters due to volcanic action, or were they due to impact? I was on the wrong side.
I think so. Unfortunately, very, very rare that you're on the right side.
I was this time.
Very, very rare
I was
indeed.
badly wrong. You know, the craters are now impact structures.
I think it's the generally accepted view.
Well, we've mapped the moon fairly well, because on the edge of the moon, the edge of the Earth-turned side, it was very foreshortened. It was great fun to go around there in the days before Apollo, before great photography, and try and find things that hadn't been seen before.
This was the thing, of course, where you were doing serious work as well. And I have here your observing book, starting in 1948.
Well, my fourth or fifth, but I'll put one thing right, I must say. I've been quite innocently claiming a discovery that I didn't make. In 1948, I was observing the moon, and on the edge of the moon, I saw something I hadn't been seen before. It looked like the edge of a small mare or sea, and I called it the Mare Orientale. There's my drawing of it. And I thought then it hadn't been seen before. That wasn't any of my maps, and much later I found that it had been seen before. It's in a German atlas of 1909, with which I was totally ignorant, so I claimed a discovery I didn't make. And there's another crater on the edge there, then called Carouamel, now called Einstein.
Renamed after Einstein from an earlier name, Carouamel.
This is Einstein, right on the edge of the moon. And I thought that was new, and it may have been, I don't know, not that it matters.
I know. Your draftsmanship is very, very exceptional.
Very early days of research work.
May I read also this lovely account you left of an eclipse which took place over the 24th and the night of the 24th, 25th of June, 1964. Oh. And this gives you a sense, I think it gives the viewers a sense of the wonderful, not only Patrick's clarity as a draftsman and communicator, but his beautiful English, even in his notebooks. I don't know what he publishes. Let me read. Of course, the main feature of the eclipse was its extreme darkness. It was a great pity that the sky was not perfectly clear. There was always enough mist around about to prevent my seeing it categorically that the moon really did vanish entirely. All I can really say is that while the stars were seen in the region of the moon, I was utterly unable to find the moon after 47 minutes past midnight.
Well, the point is, I mean, all light reaching from the eclipse moon has to come via the Earth's atmosphere. And at that stage, there have been violent volcanic eruptions in Indonesia, and there was lots of dust up there.
I think so.
Well, we have an eclipse tonight. I wonder what we're going to see. In a few hours, we'll know.
We will know.
Well, let's go back outside and see what's happening.
More than 50 missions have visited the moon. The Russians were there first in 1959, then the Americans, and the Europeans have been too. The first Chinese probe, Chang'e 1, is there right now in lunar orbit, and it sent back pictures, although we don't know much else about it. The best of the recent images, though, has come from a Japanese probe, Kagoya, which produced these amazing images of an Earthrise over the lunar surface. Just makes you want to stand there and watch it happen. Joining these missions later this year will be India's Chandrayaan-1 and NASA's Lunar Reconnaissance Orbiter. These recent missions are all in orbit about the moon, but earlier probes did land. The first belonged to the Russian Lunar series, some of which managed to return small samples of the lunar surface to Earth. The Americans had the Rangers and then the Surveyor probes, and of course we have a wealth of information from the 6 Apollo landing sites. All of these missions landed on the near side of the moon, and most of them were near the equator. To find out about the rest of the moon, scientists must resort to free samples, studying the few meteorites that have been identified as coming from the moon.
We have about 102 samples which have been blasted off the moon and then we've collected on Earth.
You're quite sure they do come from the moon?
We're pretty sure they come from the moon. We can look at their geochemistry, their isotopic signature and their age dates. And from this we can infer that they're very similar to the Apollo samples. They can't have possibly come from, say, the asteroid belt or from Mars. They have a really anhydrous mineralogy, which means that they were formed without the presence of water. So we know that they weren't formed on Earth because the majority of terrestrial rocks have some sort of water processes associated.
What about their ages?
Well, their ages vary. We have Highland lunar meteorites, which we believe have probably come from the far side of the moon, of which I've got one of the samples here. Let me pick it up for you. I have to wear this glove just so I don't contaminate it.
These things really come from the moon.
These really do. So this is a sample that has probably come from the far side of the moon. It's got lots of white chunks in it, which is this North-Osetic Highlands crust material. So this is a really interesting sample because these regions weren't visited by Apollo. These lunar meteorite samples give us a lot more information about the moon's geological history. We also have meteorites from the near side of the moon. We have Mare basalt meteorites, and we also have a meteorite. This is a very special meteorite, which again looks very similar to the other one. However, this has got a signature which suggests we can locate this one. We can look at the geochemistry of this rock, comparing it to geochemical data that's been derived from orbital remote sensing instruments, and we'll try and relate the two together. So this is a rock that I'm working on at the moment.
Where did that one come from?
Well, we're not entirely sure. We know it's from the near side. It's got lots of thorium hanging around in it, which is a really interesting geochemical signature. So my next job is to find out how old it is and to propose a landing site. So maybe try and find a source crater for this rock.
Katie, there's so much to be learned, and thank you for coming to us and bringing us actual bits of the moon.
Anytime.
Another way to find out what the moon's made of is to look at it in X-ray radiations. And I went down to the Rutherford Apple Laboratory with their built equipment to do just that. DKICS was designed to map the moon in X-rays. It was a novel and new instrument designed and built at RAL and sent on the Smart 1 probe, which ended its mission in 2006. The successor to DKICS is KICS, the Chandrayaan Imaging X-ray Spectrometer. It will be fitted onto the Indian satellite later this year. Well, the moon's X-rays come essentially from the sun. So the brighter the sun, the greater the X-ray emission. What exactly happens?
Well, if you think about party lighting, when you go into a room that's got ultraviolet lighting, and if your shirt has been washed with the right chemical, it glows purple. And it's exactly the same with the moon. When the sun shines on the moon in X-rays, the moon glows in X-rays, and the colour that it glows depends exactly on the chemical elements in the surface of the moon. So when the sun shines on the moon, it glows in the magnesium colour, it glows in the iron colour, it glows in the aluminium colour, and by looking at how bright each of those colours are, you can tell exactly what the moon's made of.
What were the main points you learned from DKICS on Smart 1?
The main headline success of DKICS was we were the first people to remote sense calcium on the moon. People knew that calcium was on the moon, of course. It's one of the 5 main elements that rocks are made of, and the rocks that Apollo astronauts brought back are full of calcium. But we were the first people who were able to spot it from orbit and begin to look at its distribution. That, again, is something we'll do over the whole of the surface of the moon with Chandrayaan.
What's the real importance of calcium?
In the case of the moon, where what you want to understand is its thermal history, looking at the way that the calcium combines with the magnesium and the iron in particular, and the aluminium, is going to tell you about whether the moon had one magma ocean early in its formation or whether it had more than one. The magnesium distribution, of course, also tells you that.
The KICS instrument is being tested in the vacuum chamber right now to make sure that the X-ray measurements are calibrated correctly, so we can't see it. We've now arrived in the clean room, hence this, and this is a model of KICS. This one won't actually fly, but it's exactly like the one that will, and therefore very good for demonstration. Chris, will you please take us to it?
Certainly. This is the flight spare instrument, so it's identical to the one that was in the calibration facility we saw earlier. It basically consists, as I said, it's about shoebox size or a toaster size, and we have radiation shields here, and we have a door on the front to protect the detectors from radiation. But I can just sort of open the door by hand, and you can then see the 24 detectors. And these are 8 swept charge devices, and so these actually detect the X-rays. But swept charge devices are very sensitive to light. So what we have to do is we have to cover them up. And we use a collimator structure, which is a bit like blinkers on a horse, so you can only look forwards, otherwise it would pick up X-rays from everywhere.
The success of KICS is another feather in the cap for British engineers and scientists. When they finish mapping in X-rays, we see the moon in a whole new way.
That's still that Ali bar, which I still have to give I've got a bit of Ali bar.
John, I'm delighted to see you as yourself this time, not me. Well, eclipse of the moon's up there, but I can't see it, can you?
Not at the moment. These clouds are being a little bit stubborn, aren't they? They're playing with us at the moment. A few hours ago, the sky was only misty and you got this lovely hazy view of the moon, but now the clouds have thickened up a little bit. Occasionally you get a glimpse, don't you, which gives you a
We do at the moment, because when the moon is fully eclipsed, you wouldn't see that.
We need one of those sky vacuums we were talking about to get rid of the clouds.
Let's see what people have been doing. Let's go around this way. Hey Bruce, we thought we'd have a look at some of your pictures, and wow, that's a stunning one.
Wow, that is nice. Whereabouts on the moon's that?
Well, this is on the moon's central meridian, the Ptolemaeus chain. So Ptolemaeus, Alphonsus and Arzakel.
They're really beautiful. That central crater is amazing. You can kind of see down the bottom there's a sinuous kind of structure which looks like a lunar rill, so maybe a lava channel or something.
Yeah.
And if I look a little bit closer, there is sort of 3 rather large dark splotches, which possibly could be dark haloed craters, just from looking at it. And you can kind of see those dark halos surrounding crater structures or some sort of pits. Now, maybe we can interpret that as some sort of eruptive site. So we could be looking at evidence there of direct volcanism within this crater structure.
Well, out in the garden with the observers, and I can see the moon. Not perfectly, but sculling behind the clouds, and the eclipse has actually started, so let's hope it'll clear. Alan, you're with me now. You've got a whole battery of instruments here. But after all, why were the ancients so interested in eclipse timing?
Eclipses were very important because in early planetary calculation it was the only time they knew for certain that they had the Earth, the Sun and the Moon exactly in a straight line. And so that was a crucial part of doing your mathematics, as it were. But then where was the actual Moon? Well, what you did initially, you used a quadrant, which is a quarter circle like this. And this is based on an instrument by Tycho Brahe. Yes, so this is designed in about 1600. You would then took the altitude of the moon before the eclipse started, and you would keep observing right through the eclipse, and you'd have an assistant to record the rising of the degrees. Now this would then give you a sort of geometrical profile of the eclipse. So that was one crucial way of finding your time. Now I've got here a pair of replica telescopes of the early 17th century. Now this is very similar not only to one that would have been used by Galileo, but more importantly, to England's very own Thomas Harriot.
Yes, the first man to look at the moon.
Precisely. 26th of July, 1609.
Long before Galileo.
Beat Galileo by 6 weeks. Now that would be the type he would have used, but if you would look at the moon through that, you would actually find a very, very tiny field. It was a very, very small field called the Galilean. But a few years later, in Germany, Johannes Kepler developed the kind of refractor we have today with a positive lens and a positive lens, and that would give you a much bigger, brighter and sharper image of the moon.
It does too.
All of a sudden, you realise that the moon seemed to be like the Earth. It had what they thought were seas and continents and features and mountains. People even were speculating, are there beings, intelligent creatures living on the moon? And all of a sudden you had this tremendous thing that broke loose after 1610. And so when you start to have eclipses, especially after that date, you're also asking another big question. What is the force that makes the moon go round the Earth? And this, of course, came to fruition with Newton.
Well, the moon has been studied since a very ancient time, but apart from briefly in the Apollo missions, there has been no life there. But now, men are going to be sent back to the moon.
Lunar Reconnaissance Orbiter is NASA's next large mission to the moon. For the first time in decades, serious plans are being made for manned exploration of our nearest neighbour. NASA dreams of moon buggies and moon bases, with a constant presence established on the lunar surface. But any pioneer going somewhere new would want to know what's out there before they set off. Lunar Reconnaissance Orbiter will supply the maps for the conquest of NASA's new frontier.
When we sent people to the moon on Apollo, our objective obviously was to get human beings safely to the moon and back, learn something in the process. And they focused on the equatorial regions, and we actually have pretty good maps of equatorial regions. We do know now that almost certainly the places of interest to go when we return and want to stay are near the poles, and our maps of the poles of the moon, our knowledge of them, of the entire moon is actually quite poor. I mean, for example, if a given feature on the moon in the polar region, a large boulder that certainly you wouldn't want to land on, our ability to know within where that is only good to a few kilometers. I mean, that's not very good. Those aren't really very good maps.
So what's LRO going to add to the picture?
There's a lot about the moon we don't know, and in fact, we know certain things about Mars better than we know about the moon. For example, the shape. We were talking earlier about models and whether you can make a model of the moon. And really, we can do much better with Mars now than we can of the moon. We have a set of camera with a narrow angle camera which gives us very high resolution images, black and white images of the surface.
How high a resolution?
About 0.5 meter resolution from a 50-kilometer orbit.
Which is notable in that that kind of resolution will enable, for the first time, we'll be able to resolve the Apollo landing sites.
That's fantastic. So you should see the lunar modules.
We should see the lunar modules, the tracks of the rovers and such.
Is this the definitive moon map after LRO?
I think it's a fair statement to say we will make the definitive moon map that will be used to enable people to return. Now, that moon map will also be richly filled in and augmented by these other international missions we've talked about. But our goal is we provide a sufficient set of detailed maps to get people back to the moon.
I'm here at the Goddard Space Flight Center to see LRO under construction. The team are working hard to make sure everything is on schedule, and today they're seeing how the propulsion system is shaping up.
But when we integrate the PDE to the propulsion module, I was thinking that we could start with just doing the PDE to the CNDH and the PSC first.
Before being attached to the spacecraft, each part of LRO must undergo shake and bake. These tests are designed to make sure that it will survive launch and cope with the extremes of temperature it will encounter in space.
All right, Chris, where we are is we're building the spacecraft structure here. This is the actual spacecraft structure.
And this is it? This is the real thing?
This is the real thing. Isn't it beautiful?
It's fantastic.
And we'll be putting all kinds of good stuff all over the spacecraft that will, our instruments, our solar arrays, our comm system, everything that it's going to take to make the spacecraft whole so that when it gets to the moon, it can send us all the data back that we need to tell us about what is really on the moon.
Apollo 11 came close to disaster when their landing site turned out to be covered in boulders. Once LRO has done its work, astronauts will know the position of every rock and crater before they try to land on the moon.
Okay, Houston, Tranquility Base here. The Eagle has landed.
The next step on my quest to go back to the moon is NASA headquarters in Washington, D.C. It's here that the biggest changes since the advent of the space shuttle are being planned. It was in 1972 that the last man walked on the moon and the Apollo missions came to an abrupt end. Now, more than 35 years later, NASA has ambitious plans to go back. This is the future for space exploration. The project is called Constellation, and it starts with the development of the Ares rocket, which will soon replace the space shuttle. The plan is to go much further than the International Space Station. The Orion capsule carrying the astronauts will dock with the Altair lunar module and another rocket stage in low Earth orbit and head off to the moon. The Orion will then remain safely in orbit while the astronauts descend to the surface. After starting his career on the Apollo program, Doug Cook was responsible for developing the space shuttle and is now leading the effort to produce the next generation of spacecraft, Ares and Orion.
We went to the moon during Apollo to figure out if we can really do it. I mean, it was really a test to see, can we actually achieve this? This time we're going back to actually accomplish longer-term goals once we're there, in terms of gathering science, in terms of perhaps developing resources that exist at the moon, but to do broader exploration. Those missions were very short, about 3 days, and these could be months. And so there's much more opportunity to learn. At the same time, we're learning how to live and work in a hazardous environment. We plan to use this to prepare ourselves to go to Mars, which is a lot farther and a lot longer trips, and so it's important that we develop these capabilities now.
So what is the plan?
First, we are building a rocket that will take astronauts back into space once the shuttle is retired in 2010. It's called Ares 1. There's also Orion, which sits on top of Ares 1, which carries the crew. The larger vehicle, Ares 5, will be developed to carry the bigger pieces of hardware, lander, the Earth departure stage, the stage that actually is required to get us out of low Earth orbit, with both the lander and Orion.
It's an Apollo-style program. What was the motivation for doing that rather than developing something out of the shuttle concept?
The primary reason is physics. Low Earth orbit, where we fly currently, is one that's suited to winged vehicles where we can come back and land on a runway. The velocities that we enter the Earth's atmosphere at are much less than the velocities that you enter the Earth's atmosphere from the moon. Wings don't work. You'd have to have materials that we are not capable of producing at this point. So blunt shapes at high velocities work better than a winged vehicle.
The ultimate aim is to build a moon base. Looking at these animations, it still looks like science fiction, a reminder there's a long way still to go before men return to the moon. My last stop was the Johnson Space Center near Houston, Texas. Alongside the reminders of past glories like this enormous Saturn V rocket, this is where astronauts train, preparing for the last space shuttle missions to the International Space Station and for an eventual trip to the moon. Outside on a rather foggy Texan day, we were given a preview of the lunar buggy for the 21st century. And it was here, seeing actual equipment being developed for use on the lunar surface, that I came closest to believing in NASA's vision.
It's a mobility chassis, it's a prototype of what you would use on the moon to move hardware around on the surface of the moon, but also to move people around. It has a lot of agility in it. The wheels can turn in 90 degrees so that you can drive at 90 degrees to your original ground track. It can raise and lower itself so that you could drive under an object, jack it up and pull it away and relocate it, such as an outpost element. You can put a pressurized cab on it to turn it into a pressurized rover.
So and then live inside it.
And then live inside it and do remote traverses and stay out for long periods of time.
This will do a lot more than a robot would do on the surface.
That's right, but I should point out, we would arrange so that this vehicle could be driven robotically. The crew could, in principle, remain in the outpost and drive this off to some site and allow it to perform tasks with remote control from the outpost.
So you could, if a cargo vehicle lands,
Exactly.
You can send this off to going there.
Exactly, and if there's no crew on the surface of the moon at that time, it could actually be controlled from Earth too, and you could have it unload and deploy cargo elements, and then
you could build your outpost.
They'd be ready for the crew to arrive, and they'd be ready to go. If you build an outpost at one site and you don't have mobility, you only have the walking range you have in the suit, which is about 10 kilometers. You're going to learn everything about that 10-kilometer area in no time, in about 30 days. And after that, what are you going to do? So you must have extended range capability, and so that means you need to be able to go out on a traverse and stay overnight.
Attaboy, swinging around there, and you're going to see a spectacular place. Boy, oh boy.
The problems of being on the moon aren't just confined to craters and boulders. It's a very hostile environment.
There's no atmosphere. You're in a vacuum all the time. You can't just go outside easily. You have to don complex, life-preserving gear that has to work all the time. The lunar surface, the dust of the lunar surface, the dirt, if you like, we call it regolith, is actually quite a toxic material. It's been generated through bombardments over billions of years. These are very sharp particles. They play havoc on equipment like this when it gets into bearings and things like that. So you've got to have very sophisticated sealed bearings and things like that. Another problem with the dust is potentially it's actually toxic to humans if you inhale it. So we're going to have a lot of mitigation to keep the dust out of the human environment, and the suits are going to have to be very dust tolerant. Another problem that we're going to have on the surface of the moon unquestionably is going to be the radiation environment. There are two kinds of radiation effects that we have to protect the crew for. One is the solar proton events. Fortunately, those are predictable and you can shield.
And you can see them coming.
And you know they're coming, you get warning, and they don't last long. The more serious radiation is what's called galactic cosmic radiation. It's the background radiation that's all through space. We're protected from it here on Earth by the Earth's magnetic field and the atmosphere. We're going to have to understand how that radiation affects the human body a lot better if we're going to have people on the surface of the moon for very long periods of time, like 6 months.
Many small steps remain to be taken on our way back to the moon. But just imagine this: an astronaut standing on the edge of Shackleton Crater, bathed in the rosy glow of a lunar eclipse. Back in Patrick's Garden, the eclipse is almost upon us. We've switched to our infrared camera to avoid annoying our astronomers. But with minutes to go before the moon completely enters the Earth's shadow, disaster has struck. The clouds have thickened, blocking our view of the moon entirely.
You stand around looking at that telescope on the sky and saying things like, tut tut, dear me, and how annoying. I'm afraid all we can do now is just wait and hope we do have another 50 minutes.
Can you see anything at all?
No, I don't know, but I don't know about the colour.
I've been looking at the moon now ever since 1930, and it never ceases to amaze me.
I think there's still things that we're going to learn about the moon. It's not often these days, I confess, that I turn my telescope to it. But every now and again I go and revisit old haunts.
I did have a review there. I mean, I've got a fairly big scope, got my 15.5 inch, and as long as I could, the first thing I looked at all the time was the moon.
I just saw the silhouette of a figure.
It's getting a bit hazy then.
Well, 1 minute past 3, the eclipse is now total. Unfortunately, so is the cloud. Had a very brief glimpse to partial cloud a few minutes ago, and we thought that the eclipse part looked a very dull greyish pink, but you couldn't really tell.
It can't stay cloudy for the whole 50 minutes, can it?
It can, you know, but let's hope it doesn't.
Oh, there you go. It's definitely slightly pink, isn't it?
See,
Oh, that's better.
There you
Fill
go.
out quickly.
That's better.
Is there a pinky bit to that?
Yeah, definitely. With the Sky at Night camera, we can just about catch glimpses of the eclipsed moon through the clouds, but it's not a brilliant view. The astronomers should have better luck with their digital cameras. All they need is the briefest clear patch to get the perfect image.
That's better.
Whoa. Feet up for a second.
All right, so. But the camera's picking it up quite nicely. There's a nice little orange eclipse moon in there, and Saturn.
Is that your official colour chart? It's orange, is it?
The other camera with the larger telescope on it's definitely picking it up as orange. Yeah.
Yes, it's just these faint glimpses through the clouds. You look around the clouds and you see sort of thinner patches, and you just hope that one of those will let the eclipse be visible.
That's the best we've seen it so far.
At the moment, it's looking fantastic up there. Nice clear view of it, looking nice and red.
It certainly looked to me a little earlier when it was very clear as a very deep rusty colour, not maybe as dark as some eclipses have been, quite bright. Can't keep a good eclipse down.
Yeah, this one came through in the end.
Yeah, definitely.
Totality is just ending now. We can say quite definitely that was a very bright eclipse.
Very bright indeed.
We weren't totally beaten.
No, I think we won on points.
So look,
the base of the moon is actually quite.
That's rather nice.
That's
okay.
It's the mist actually adds something to it, I think.
Mostly mist, but yes, I admit it's added something.
Well, I'm afraid that's the end of our eclipse watching tonight. But after all, we've been looking at the moon, and so much is happening there. We're going back there. We may set up bases there. There's so much ahead of us, and the moon, after all, is a wonderful world full of surprises. But so far as the eclipse is concerned, it's now totally concealed. Totality is over. So let's look forward then to the eclipse of the year 2015. Perhaps we'll reconvene on my salty lawn then. So, for the moment, good night.